Imagine you're looking at a blueprint for the city of the future, a hyper-connected metropolis where millions of citizens move in perfect, synchronized harmony. There are no traffic jams, no communication breakdowns, and no central command center. Every inhabitant knows exactly where to go, what to build, and when to defend. To build something this efficient, we'd need billions in Silicon Valley funding. We'd need 6G fiber optics, advanced AI swarms, and a network of autonomous drones. In our modern world, we call this the smart city, the ultimate dream of urban engineering. But while we're busy patenting the technology to make it happen, it's already functioning right beneath your feet. Step off the pavement and look into the dirt. You aren't looking at a nest or a hole. You're looking at a biological megacity that makes New York look like a disorganized village. We've been conditioned to see the ant as a mindless pest, something to be swatted away or stepped on without a second thought. We see them as squishy little bugs driven by primitive instincts. But modern entomology and materials science are beginning to pull back the curtain on a different reality. What if I told you that these bugs are actually high-performance units encased in biological armor? What if their silent world is actually a chaotic broadcast of acoustic data? When you look at the specs, you realize the truth. The ant isn't just an insect. It is a masterpiece of distributed computing and structural engineering that thrives in a world of high-impact physics. Welcome to the Proof Vault. Subscribe, because this episode might just change the way you see the dirt beneath your feet. There are more than 20 quadrillion ants alive at any given moment, outnumbering humans by a margin so large it's difficult to even picture. If you were to weigh them all together, the total mass of ants on Earth rivals that of humanity itself. And they didn't get here by accident. Ants have existed for tens of millions of years, surviving mass extinctions, climate collapses, and the rise and fall of entire ecosystems. Long before human cities, roads, or agriculture, ants were already building societies, complex, adaptive, and remarkably resilient. But how does a creature this small survive a world this big? To understand that, we have to look at their specs. In engineering, if you want a structure to survive for millions of years, you don't build it with soft, vulnerable skin. You use exoskeletal engineering. Instead of an internal skeleton like ours, the ant is encased in a high-tech suit of armor made of chitin. This isn't just shell, it's a long-chain polymer that mirrors the carbon fiber composites used in the fuselages of a Boeing 787 or a SpaceX Dragon capsule. It's incredibly light, yet pound for pound, tougher than many metallic alloys. But there is a specific trade-off in materials science. The harder a material is, the more brittle it becomes. Think about a luxury sapphire crystal watch face. It's nearly impossible to scratch, and you can't squash it like a piece of fruit. But every material has a failure point. When you subject a piece of glass or a high-tech ceramic to extreme concentrated pressure, it doesn't bend or bruise. It fractures. Engineers call this brittle failure. In plain English, it shatters. This is the shatter versus squash factor. When we step on an ant, our eyes tell us we are squashing a bug. But under a scanning electron microscope, the physics reveal a different reality. You are witnessing the structural collapse of a biological glass. The ant doesn't have a circulatory system that bruises or skin that tears. Instead, its chitinous shell sustains microscopic, jagged structural fractures. It literally cracks like a porcelain plate or a smartphone screen. For centuries, we assumed crushing was just a generic term for killing an insect. But in the world of materials science, the ant is a crushable object in the most literal technical sense. It is a biological machine designed to be unbreakable until it hits its limit and shatters into shards. Building a glass soldier is one thing, but how do you command 20 quadrillion of them? For a long time, science had a simple answer: smell. We were taught that ants communicate through pheromones, chemical trails left on the ground like a series of post-it notes. But in the fast-paced world of modern warfare or emergency evacuations, chemical trails are the equivalent of snail mail. They are slow, they dissipate, and they can't convey complex real-time warnings to a massive crowd in seconds. To achieve that, you need a fiber optic network. You need sound. Under high magnification imaging, we've discovered that ants are carrying a piece of specialized acoustic hardware on their bodies. Located on their abdomen is a structure called a stridulatory organ. It consists of a file, a series of microscopic ridges, and a plectrum, a hardened scraper. By rubbing the plectrum against the file, the ant doesn't just make noise, it performs a high-frequency broadcast. It's essentially a built-in cello or a biological radio transmitter. For decades, we thought ants lived in a silent world. But researchers at the University of Turin used ultra-sensitive microphones to listen in on these silent colonies. What they found was a chaotic, sophisticated symphony. The ants weren't just reacting to chemicals, they were vocalizing. They used different rhythms and pitches to signal everything from the quality of a food source to an urgent red alert. These acoustic waves travel through the soil and the air, allowing an ant to broadcast a specific warning to thousands of its peers simultaneously. They aren't just drones, they are a synchronized military unit with a real-time comms link. But communication is useless if you don't have a place to take cover. When an ant broadcasts a warning to evacuate, they aren't just running into a hole in the dirt. They are retreating into one of the most sophisticated pieces of civil engineering on the planet. Think of an ant colony not as a nest, but as the Cheyenne Mountain Complex, a nuclear-hardened bunker designed for absolute survival. When we look at a skyscraper, we marvel at the HVAC systems, the massive fans and ducts that keep the air breathable. Now, consider the ant. In a colony with millions of inhabitants, the sheer amount of CO2 generated should, by all laws of physics, suffocate every ant in the lower chambers within hours. Yet they never run out of oxygen. The ants have engineered a passive ventilation system that rivals the best green building tech in London or New York. By building specific mounds and internal shafts, they utilize the Venturi effect. As wind blows over the surface of the colony, the change in air pressure naturally sucks stale CO2 out of the exhaust vents and pulls fresh oxygen deep into the intake tunnels. It is a self-sustaining, zero-energy, smart home HVAC system. When an ant issues a command to get into your dwellings, it isn't a random panicked instruction. It is a strategic move to pull the population off the exposed surface and into a climate-controlled, oxygen-rich, reinforced bunker. They aren't just running for their lives, they are executing a highly engineered emergency protocol. If the ant's body is the hardware and its bunker is the infrastructure, then we have to ask, what is the operating system? When you look at a single ant, its brain is roughly the size of a grain of salt. Individually, it lacks the processing power to map a continent or design an HVAC system. So, how does a creature this small perform what looks like complex calculus? In the world of computer science, we have a name for this: distributed computing. Think of a modern server farm or the blockchain. There is no CEO computer making every decision. Instead, you have thousands of individual processors working in parallel. This is swarm intelligence. The colony functions like a decentralized server. Every single ant is a mobile sensor, constantly uploading data to the cloud of the collective. When one ant detects a change in air pressure, the telltale sign of an approaching storm or a giant's foot, it doesn't wait for orders. It broadcasts the data. The network processes this input and triggers a system-wide response instantly. This creates what engineers call a self-healing network. In a luxury SUV, if the CPU fails, the whole car dies. But if you remove 10,000 ants from a colony, the colony doesn't skip a beat. It reroutes tasks, recalibrates its sensors, and continues to function. We see this in living engineering, where ants link their bodies to form rafts during floods or bridges to cross gaps. They are calculating stress, tension, and fluid dynamics in real time using nothing but collective feedback. They are a single, massive biological supercomputer. Let's be honest with ourselves. As modern thinkers, we pride ourselves on our tools. We needed the scanning electron microscope to finally see the brittle fracture mechanics of the ant's exoskeleton. We needed ultra-sensitive acoustic sensors and the research labs of the University of Turin to realize that ants aren't silent, that they are actually vocalizing in a sophisticated, synchronized network. Without our 21st century technology, we were blind and deaf to the true engineering of the ant. But this is where the logic trap closes. 400 years ago, in a pre-scientific world without microscopes, without laboratories, and without a clue about materials science or acoustic engineering, a text was produced that describes a very specific, almost technical encounter. It depicts a valley of ants. As an army approaches, one single ant, acting as a sensor for the collective, recognizes the threat. It doesn't just leave a chemical trail, it vocalizes a warning. It commands the colony to retreat into their dwellings so they aren't crushed. Now in English, crushed is a generic word, but in the original text, the word used is yabtimanakum. For centuries, linguists were puzzled. This specific Arabic root, HTM, does not mean to squash, to kill, or to flatten. In every other context of the language, it is used exclusively for shattering glass, breaking porcelain, or fracturing brittle materials. Critics and skeptics laughed. Why use a word for breaking glass to describe an insect made of flesh? Today, we have the answer. The text wasn't using a metaphor, it was using a technical spec. It was describing the brittle failure of a chitinous exoskeleton with a precision that we have only recently confirmed through materials science. So here is the question for the skeptic. How did a man in the 7th century desert know that an ant's body behaves like biological glass? How did he know that a silent insect actually possesses a sophisticated acoustic communication network? If this was just ancient folklore, why is the terminology so pinpoint accurate to the physics of the 21st century? Did he have a microscope, hidden in the dunes? Or are we looking at a source of knowledge that exists outside of our linear timeline? You can ignore the message, but you cannot ignore the engineering. The evidence isn't hidden. It's been under your feet the whole time. How did a text written 1400 years ago know what modern science has just now discovered? The Proof Vault, where science and history meet knowledge. Subscribe, because the next episode might just change the way you see science.